Alkenes are molecules that have the carbon-carbon double bond functional group. Each carbon will have two other things bonded to it. If there aren't any other functional groups, alkenes are hydrocarbons, meaning they're compounds that have only hydrogen and carbon. Before I talk about the structure, let's take a look at some examples. The very smallest alkene is ethylene, 2 carbons, 4 hydrogens. Ethylene plays the interesting biological role of causing ripening in fruits. In fact, often fruits are picked when they're unripe and sprayed with ethylene just before they go to the grocery store. That resumes the ripening process. Industrially, millions of pounds of ethylene are made every year. It's used as a synthetic intermediate to make many things, but its major use is to make polyethylene, a long molecule that has many units of ethylene tied together. Polyethylene is the most common plastic. It's found in plastic bags, packaging, water bottles, all kinds of things. Its larger cousin, propylene, has 3 carbon atoms, and, like ethylene, is used to make large quantities of a polymer, polypropylene. Polypropylene is a better plastic than polyethylene. It's stronger, it makes better packaging and films, it can be used to make clothing, electrical insulation. A large number of car parts are made from polypropylene. Polyvinyl chloride is another polymer that's widely used in the construction industry. It makes a very rugged, durable plastic. It makes it ideal for construction parts like pipes and structural materials, even furniture. Beyond these industrially used small alkenes, there are other interesting alkenes. Alpha-farnesene, for instance, is found in insects. It's used as an alarm pheromone to warn other insects of danger. And, interestingly, it's found in the skin of apples. It presumably functions by protecting the apples from certain insects. And an isomer of alpha-farnesene, which also has 4 double bonds, is beta-farnesene. Beta-farnesene is the same structure except that the double bond is in a different place, and it's also used by insects as an alarm pheromone. So there are all kinds of interesting alkenes. Let's take a good look at the structure of the double bond itself. You know that there are a variety of theories about bonding, and the very simplest one is called the Lewis theory of bonding. It simply depicts the sharing of electrons to make filled outer shells. In this theory, the carbon-carbon double bond is made up of 2 carbon atoms that share 2 pairs of electrons. They're simply shown as 2 pairs of dots in between the 2 carbon atoms. So the double bond is written as I've shown. I've used the X, by the way, to indicate electrons that are contributed by hydrogens. This is the structure of ethylene, and the carbon-carbon double bond is its central element. But although this structure theory tells us that the carbon-carbon bond is made up of sharing 2 pairs of electrons, it doesn't tell us anything else. Nothing about what the structure looks like, nothing about where the electrons are, nothing to give us a hint about the chemical reactivity or the shape of the molecule. So Lewis bonding theory falls way short. The valence bond theory tells us much more. Remember, the valence bond theory suggests that bonding results from the overlap of orbitals. A carbon that has 3 things bonded to it, like an ethylene carbon, is sp2 hybridized, so it has 3 sp2 orbitals used for bonding. I've shown outlined in blue the sp2 orbital of one carbon overlapping with an sp2 orbital of a second carbon to make a sigma bond. A very important point is that this sigma bond is symmetrical about the axis I've drawn that connects the nuclei of 2 carbons. This means that there can be complete free rotation about that bond. When we make the double bond, all that changes. Take a look. The double bond is formed by the overlap of a p orbital on one carbon with the p orbital of another carbon. Remember, these carbons are sp2 hybridized, so they each have a p orbital left over. Before I draw in those p orbitals, I want to point out that all of the atoms I'm shown here are in the same plane, a plane that I've represented here. When that's the case, those p orbitals are perpendicular to the plane. A lobe of each p orbital sticks up perpendicular to the plane, and the other lobe sticks down perpendicular to the plane. As a result of this orbital arrangement, when we show the electrons that are involved in bonding, remember there are 4 electrons involved in this bonding, 2 in the sigma bond and 2 in the pi bond. When we show those electrons, they look like this. A pair is in the sigma bond, and there are 2 other electrons. Those guys are in a pi bond. They're in a pi bond that holds the 2 carbons together because those p orbitals can overlap, represented by this. I basically have shown a bunch of lines to represent the space between those p orbitals, the regions in space in which those two electrons can be found. This is the pi bond, and notice, it's above the plane of the other 6 atoms, and it's below the plane of the other 6 atoms. It's never in the plane, and it can only happen if all of those 6 atoms themselves are arranged in a plane. If there were rotation about that sigma bond, those p orbitals would not be parallel, they wouldn't overlap, and we couldn't have a pi bond. So rotation would cause the pi bond to break. That doesn't happen because it takes an enormous amount of energy. The result? The carbon-carbon double bond is rigid. All of the atoms I've shown, all 6 atoms, are held in a fixed orientation relative to each other. Now there's nothing special about that fixed orientation of all 4 atoms attached to carbons or hydrogens. But what if we have something different on each carbon? I'm going to put chlorines in the place of 2 hydrogens. One of the orientations for these 2 chlorine atoms is to be held on the same side of the double bond, as I show here. The chlorines are on the same side, and the hydrogens are away on the same side. The chlorines stick out toward us, and the hydrogens both stick back. Those 4 atoms are held in that fixed arrangement. There's a second fixed arrangement that's possible. One of the chlorines toward us, and the other one back. Take a look. So this is a second orientation of atoms where all the atoms are bonded to each other in exactly the same order. The only difference is that they have a different spatial arrangement. This is our definition of stereoisomers. So alkenes have stereoisomerism. There are 2 main ramifications of this pi bond, and one of them is the fact that it holds these atoms in a rigid arrangement which gives rise to stereochemistry. The other thing that this pi bond dictates is its chemistry. Even the Lewis bonding theory structure suggests to us there's an extra electron density between the 2 carbon atoms. And when we look at the pi bond of the valence bond theory, we see very clearly the extra electron density is highly available. It sticks out away from the other atoms, above and below the plane. This lets us already predict the chemical reactivity of an alkene. It suggests, correctly, that alkenes react with reagents that are seeking electron density, reagents we call electrophiles. In other videos, I'll elaborate on the stereochemistry of alkenes and the reactions of alkenes with electrophiles. Finally, let me point out that we can view pi bonds in the context of molecular orbital theory. Molecular orbital theory can help us explain some things that we couldn't explain by valence bond theory. But this isn't important for most of our discussions about pi bonds, and I'm going to save talking about molecular orbital theory of pi systems until we really need to know it.